Hello and welcome to the Our Connected World podcast brought to you by TE Connectivity. I'm your host, Michelle Dawn Mooney. Today we're talking about transforming vehicle architectures. I have a great guest to bring on for the conversation. Lamar F. Ricks is Senior Director and Chief Technology Officer, Sensors for TE Connectivity. Lamar, thank you so much for being with me today.
Yeah, my pleasure, Michelle. Excited.
Yeah, I am excited as well. I'm looking forward to getting into the conversation because there's lots to talk about, a lot of new things happening, and you're really in the mix of it all. Before we kind of get into the Q&A, can I ask you to give a brief bio if you can?
Yes, you sure can. So as you said, I'm Lamar Ricks. I'm the CTO for Transportation Sensors Engineering in the TE Connectivity Sensors Group. And I've been with TE now for about 4 years in that role. Prior to that, I was with another large company as CTO of about $1 billion sensor business. I've done sensors my entire career, technology development, platform development, product development, many different roles. And sensors is kind of in my.
Yeah, I guess so. So we have a lot to talk about. And at the top of the podcast, I already mentioned there's so many changes, really cool things happening in this field. So let's start off here. How have advancements in smart vehicle technologies such as autonomous driving reshaped vehicle architecture design?
That's a great question. So there's a lot of trends that are happening right now. And those trends are really around electric vehicles, hybrid electric vehicles, as well as plug-in. So it's really about electrification. And some of the dynamics, things like urbanization, pressures for sustainability becoming green, all of those pressures have encouraged governments around the globe to drive various legislation, new regulations, things of that nature. All of that is benefiting the OEMs to drive electrification. And then there's various tax incentives that have really motivated those consumers to adopt electrification. And the change is happening very quickly. Vehicle architectures are moving towards something called the zonal approach. And that zonal approach has standardized electrical and electronics-based platforms. And this standardization and modularization of those electronic systems is paramount to the success of EVs. And it promises a lot of different benefits. Promises cost and weight reductions, ease of interchangeability of subsystems and components, as well as driving more advanced features in those vehicles. And this quick pace of innovation for high voltage propulsion systems is driving different architectures in the vehicle. It's actually driving a complete radical rethinking and redesign of low voltage electrical and electronic systems in those architectures and the various platforms that are associated with it. There's some vehicle programs that have already shifted from the legacy distributed architecture to a domain-centralized architecture. And those domain architectures are now going to have to go through yet another change to the zonal architecture, which is really optimized for the future EVs. And that includes complex high voltage systems that do power the vehicle and allow for those automated driving functionalities. So the old systems were legacy distributed architectures. They migrated to more of this domain centralized architecture. And now in the future, they'll be moving to a zonal architecture. There's a few percent of the vehicles that are already leveraging zonal architectures, and that's some of the leaders within the industry. But it's estimated within less than 10 years, approximately 40% of the OEMs are going to be on the zonal architecture. The trend is really pushing competitors to keep up and quickly adopt with those changes. Today, the OEMs of the electrified vehicles utilize software not only to improve safety and comfort and features like infotainment, but also that helps to enable increased electrification and those ADAS features. In the future, vehicle functionalities and all the related software is going to be developed independently from the hardware on which it operates, and it'll be updated all throughout the entire vehicle lifecycle, thus leading to something that is called the software-defined vehicle, or SDV as it's sometimes called. We are actually participating in this drive towards ADAS and improved functionality. And one recent platform launch that we had was a high-resolution wheel speed sensor. And that wheel speed sensor has over 4 times the resolution of legacy wheel speed sensors. This higher level of resolution gives finer control of wheel movement and allows automation of various functionalities such as automated parking and even traffic jam maneuvering assistance. It's really driving vehicle functionality to a completely new level.
Yeah, that definitely sounds good, especially with the traffic jams, right? We could all use a little help there. So I want to ask you, and you touched briefly a few times about zonal architecture and some of the benefits there, but let's dive a little deeper. Why zonal architecture versus domain centralized architecture?
Great. So the domain architectures really enable systems to be, I'll say, logically organized, and it's pretty suitable for cloud connectivity. So, for example, infotainment, ADAS, telematics, gateway systems are all grouped, and each has its own electronic control unit. However, that architecture actually increases the amount of wiring and connections in the vehicle. What that does is it increases the vehicle weight, the cost, and although OEMs can easily introduce new functionality with that type of architecture by adding new sensors, new electronics, and even an ECU to control all of that, that plethora of increasingly interconnected ECUs within the overall system, it's kind of costly, and it also brings about this threat of cyber attacks due to multiple potential digital access points from external. So as a result, these domain centralized architectures that are currently pretty dominant ultimately are not the most efficient way to organize a vehicle electrical system. Therefore, a revision of the system's core architecture and the electrical distribution system, it's a must. And it's leading to the mass adoption of this zonal architecture. And with the zonal architecture, systems are then logically and physically grouped into these efficiently organized zones. And in each zone, all systems are managed by the same processor. They have their own power distribution unit. They're all connected to the Ethernet via a gateway, and then ultimately to the central vehicle computer. And then just a few ECUs can manage the entire vehicle, while at the same time delivering all this new advanced complex functionality that the vehicles have within them. So in a zonal architectural based system, because the ECU is closer to the actuators and the sensors, less wiring and fewer connections are even required. So the end result, it's a leaner, much more efficient and scalable design, and enables efficient connectivity, reduce weight, significantly reduce costs in the vehicle systems, and much more robust cybersecurity and improved reliability. So the zonal architecture promotes this really well-structured, clean, safe environment that you can really drive software in the software-defined vehicle. So you'll see things like over-the-air updates, like you would even see with your cell phone, subscription services, all of this kind of thing. So the move towards zonal architecture, it's going to make the vehicle almost like a supercomputing smartphone on wheels, allowing drivers to optimize their experience with just downloading apps. And you may ask, what's that mean for sensors? So in some of the vehicles today, there's sensors that have, even yet today, analog outputs, and they're fed into analog to digital converters that are located on the electronic boards of the customer's local control unit. In the future, I expect to see predominantly sensors with digital outputs communicating on this inherently bus-based system, leveraging the zonal architecture.
So let's talk about that because, as you said, so many things happening and very quickly when it comes to sensors. So, what impact have these technological advancements had on the role and development of the sensors in vehicles?
Well, this shift towards zonal, it's really going to drive and allow the software-defined vehicle, and without it, it couldn't become a reality. So you're going to see OEMs in the future have basically a predominantly software development exercise. Historically, the OEMs and the tier ones have designed optimized hardware-centric based systems. Then they would decide, pretty much like what software is required to enable the systems. With the zonal architecture, the exact opposite is going to occur. The OEMs are first going to design and evolve the software to control the zones, and then they'll consider how the hardware needs to change and adapt to support the software. So the hardware now is actually going to follow the software. And this is going to enable a transfer of software development sovereignty from the tier ones to the OEMs. And that strict separation of hardware from software through a middle layer now enables independent software and hardware development processes and life cycles. So I would say the analogy here is probably more like early PCs that were very custom and later then adopted standard motherboards. So you're going to see a lot of analogies between vehicles today with where computers went through their journey in the past. And to make all that happen, what is really key here is standardization and modularization. It's crucial. So the OEMs are going to control most of the software development, and they'll drive towards standardization of hardware and electronic modules. This is then going to provide greater value to the auto manufacturers, enabling them to drive maximum reuse across their various platform models. With the zonal architecture, there's also going to be this migration to a 48-volt system to support the system's higher power consumption requirements and also the redundancy. And those 48-volt systems, they have less power loss. And the key thing here is that then enables much lighter wire harnesses. So in today's systems, you'll have a vehicle that has pretty large cabling and a lot of different cabling all throughout the car. With the zonal architecture, you're going to see much fewer cable assemblies, and they'll be much lighter and easier to route throughout the vehicle. So then the overall benefit to the OEMs from migrating to the old architectures to this new zonal architecture is actually going to be significantly reduced development costs, significant reduction in the capex required for their factories to produce, significantly increased manufacturing efficiency, faster development cycle times, reduced inventory, all kinds of great benefits are going to come out of this. It's going to be tremendous for the OEMs. And with the smaller and shorter electrical wiring and sensors, with the digital outputs, it's going to make it even easier for OEMs to add and subtract sensors to pretty much tailor the functionality targeted for each vehicle. In fact, the economical drive they're going to have for trying to even combine multiple sensors into one package, like something that you would refer to as combi sensing, that's typically done to minimize the cost of packaging or the associated complex cabling assemblies, that may actually reduce and go away because it's going to be easier to add and subtract individual sensors in the future. And additionally, there's also this ever-increasing need for a mature understanding of functional safety requirements. Every organization around the globe pretty much has to have a trained and certified functional safety manager, or several actually. And also engineers and IC designers, they all need to be really well versed in the topic of functional safety. Functional safety, I'm not sure if you're familiar with it, it's referring to a safety integral or safety integrity level, SIL. And a SIL applies to a safety function from start to finish, and it pretty much affirms that the system is reverting back to a safe state or performs properly even during incorrect operation or a loss of functionality. It's in-fault tolerant architecture. So both the design and the process for product development must follow functional safety standards. And these are commissioned by the International Electrotechnical Commission, IEC, and governed by things like IE 61508 and also ISO 26262. And everyone needs to pass these independent functional safety audits in order to achieve the corresponding quantitative metrics that assess properly that you're meeting all those safety standards. There is an ASIL decomposition. It's a technique that's used in the development of automotive systems that manages and mitigates risk, and that's associated with different functions or different components. So the process involves breaking down a system with a higher ASIL requirement into much smaller parts and functions, each of which have to be assigned a lower ASIL rating in order to meet the higher level ASIL within the vehicle. And that approach allows for more manageable and cost-effective implementation of these safety measures. So ASIL is divided into 4 different levels. There's an A, a B, a C, and a D. And ASIL D is representing the absolute highest degree of hazard control rigor, and ASIL A is the lowest. So this classification really helps in assessing the severity, the exposure, and controllability of potential hazards. And it guides the development process to focus on those critical safety measures. So ASIL A is applied to systems where the risk is relatively low, but it still requires mitigation to ensure safety. ASIL B is for systems where there's moderate risk, but requiring more stringent controls than ASIL A. Then ASIL C targets systems with much more considerable risk, and it demands more rigorous safety measures. And then finally, ASIL D, being the highest, is reserved for the most critical systems where the risk of harm is highest, and therefore necessitating the strictest of safety requirements. So all these changes are really challenging engineers to better understand the details of the end application, what's required of the sensor in the system, the role, the value of those sensors, and provides not only in terms of functionality and performance, but also in terms of safety, quality, reliability, weight, sustainability, and cost. So there's a lot of factors that engineers have to consider when they're doing product development. So as these OEMs push towards a software-defined vehicle world and primarily focus on their software, their understanding and maturity level for these mechanical systems and sensors may decrease. In the past, they were doing very hardware-centric developments, and we're really good at that. I think in the future, when we go to software-defined vehicles, more of that is going to be shifted to the tier ones and the system players as well as the sensor providers.
So, with these increasingly complex vehicle systems, what measures are being taken to ensure the reliability and then, more importantly, as you kind of hammered this word, rightfully so, the safety of sensors? Because there's so many moving parts, there's a lot involved. So, what type of levels are in play there?
Well, you spoke about reliability. So I have personally institutionalized the design for reliability engineering methodology within my R&D organization. This is globally. And design for reliability, or DFR as it's sometimes referred to, it ensures that the product performs the intended function under the specified and required conditions or loads for a defined duration and in a particular environment during which various failures can occur. So this methodology really integrates reliability considerations into the product design process, and it helps to minimize failures and enhance the overall product performance and the safety of the product. There's something called a mission profile, and a mission profile is a detailed description of the operational conditions as well as the requirements that the product is expected to encounter throughout its entire lifetime. Included in that mission profile are the functional loads, things like thermal and mechanical and electrical, and all of the environmental stresses, which all depend on the specific usage conditions of the final end application. And then commonly those inputs for the mission profile are then driven into the product requirements document. So we're utilizing this input from the customer to define how our product has to perform, and we're designing it and validating it accordingly. We need to understand the usage profile, the customer supplied data in the form of various simulations or test data or field data. We use industry standards, and all those inputs then, as well as inputs from known failure modes from the past experience we have in various products. So we have our product FMEAs and our design FMEAs for similar platforms and products, and all that goes into our product requirements definition for doing product development. That then ensures the sensor developer is developing a reliable product that will meet the requirements of the end application. And it will also help us to ensure that the product is neither over-designed or over-engineered and adding unnecessarily costs. It's optimized engineering. It's just right. And we also do functional safety assessments. I spoke about the functional safety managers and how all of our engineers are getting functional safety training. So our functional safety managers and our R&D engineers, they have deep discussions with the functional safety experts from the OEMs and the tier ones to ensure a full understanding and alignment regarding all the ASIL requirements of the sensors, as well as whatever decomposition methods are being applied at the system level. So a proper understanding of the vehicle, the system architecture, and the flow down through the subsystems and individual components and to our sensors, it's a must. And it's a very complex topic that must be handled by properly trained and certified subject matter experts.
You talked about things happening very quickly and rapidly and some exciting things at that. How do you envision the next generation of vehicles evolving?
Well, I did mention that the next generation vehicle is definitely going to be much less hardware centric than the legacy internal combustion engine based platforms of the past. Vehicles will be software defined platforms. I spoke of the software defined vehicle, and it'll have extreme levels of standardization and modularization of hardware. Um, the next generation of vehicles is really going to be differentiated around the experience of drivers and the passengers. So sensors will play a key role in that evolution, providing features and functionalities on a vehicle platform that can be tailored to the specific needs of the driver and the passengers. And the experience of the driving will be much different than in the past with automated driving, assisted functionality, and so forth. The SAE, or Society of Automotive Engineers, has defined 6 different levels of driving automation. And level 0 is fully manual, that's no automation. So the driver would perform all the tasks like steering, acceleration, uh, lane changing, braking, and so on. Those are kind of the old legacy vehicles. Level 1 is driver assistance. And in level 1, the vehicle has maybe a single automated system, things like the vehicle monitors speed through cruise control or something like that. At level 3, which is partial automation, also known as ADAS or Advanced Driver Assistance Systems, the vehicle's performing steering, acceleration, lane changing, braking, but the driver's monitoring and can still take control at any given time. Level 4 is referred to as conditional automation, and this is where the vehicle is performing all the driving, all the maneuvering functionality, but the driver still has override and in certain conditions. Level 5 is high automation. And in level 5, the vehicle is performing all driving, maneuvering, and geofencing is required. The driver still has an override in level 5, but level 6 gets to absolute full autonomy, and the vehicle is performing all the driving, maneuvering functionality under all conditions. No driver interaction is required whatsoever. And I think the idea of even being a driver in level 6 will go away because the car is the driver. So most vehicles today are operating between a level 2 and a level 3. And although the OEMs were extremely optimistic a few years ago and even forecasting a fast acceleration to level 4, most have kind of lowered their expectations because the emphasis is really on driver and passenger safety.
It really is crazy to see how things are changing. I almost feel like we're in a sci-fi movie, right? Especially when you talk about full automation, but it looks like we're a few years down the road from that. But let me ask you this. What are some of the key factors engineers should consider when selecting sensors for their next generation vehicle design? So short term, not necessarily long term.
Right. Well, there's so many key factors. Let's start with the product robustness. We spoke of that. So design for reliability and robustness validation, that's pretty much the foundation of delivering a high reliability product in the end application and a world-class experience for our customers. And those customers inclusive of the vehicle owners, OEMs, tier ones. So we talked about reliability, designing for that, and then validating that. Performance and functionality, that's obviously something that a sensor has to meet. So within TE, we're employing a design for Six Sigma or DFSS methodology, and that helps to ensure our products are fully capable and meeting the specifications and the requirements over all of the conditions of the application. Functional safety, that's another, we spoke of that earlier. Is the sensor meeting the appropriate functional safety requirements for the application? A full functional safety assessment has to be led by a certified functional safety manager, and the engineers have to be trained on functional safety. That's crucial. With standardization, the modularization we spoke of, interchangeability and standardization for a software-defined vehicle is going to be absolute key. So with the migration towards software-defined vehicles, uh, there's huge needs for standardization. It's very important to give special consideration to interchangeability. The OEMs and the tier ones will be looking to have sensors that can be easily and seamlessly changed, either in the application or even between various suppliers. Becoming green, sustainability, that's another huge topic. The most glaring challenge right now to the automotive industry is definitely carbon footprint. So these traditional materials and manufacturing processes, mostly reliant on fossil fuels, all those contribute significantly to greenhouse gas emissions, and many of those are being banned. So we have to come up with alternate materials. And some of those materials may not be as proven, or they may not even be as robust as some of those used in the past. But with the legislation banning utilization of some of those, it's becoming a challenge. So sometimes I think going forward, one of the bigger challenges for sensor engineers is going to be maintaining the product robustness with materials that are considered green. Another thing would be supply chain continuity. So, how reliable and robust is the overall supply chain for components, for materials, and even for the equipment? Is there a special single source, or are there multiple options that are available in case of obsolescence concerns? So, any geopolitical concern that would prevent easy shipment of goods throughout the supply chain, having a global footprint is really key. And that's something that we have. For example, we have resolvers for electric vehicles for e-motor position, and we have a global footprint. We have resolver manufacturing in every region that can supply our customer base. And then, of course, we have to have technical and quality support. So in automotive, driving zero defects is a top priority. So doing things like rapid root cause analysis, problem solving for driving continuous improvement and driving zero defects, that's really a key for us.
It seems like the game is really changing almost by the minute when you have this technology come into play. Can you share your insights on how TE Connectivity collaborates with OEMs to develop innovative and then customized sensor solutions?
Sure. Yeah, we engage really well in advance to product development life cycles to understand the existing pain points and the future needs of our customers. We ask them what's working, what's not working, and with our sensor expertise, we're also helping to identify things that maybe they were not aware of, so unarticulated needs. And often we're engaging in advanced developments with our key customers to develop the next generation technologies that are really going to be the heart of our sensing platforms for years to come. So, if the first time you're exposed to a new application is via a request for information or RFI or a request for quote, which is RFQ, you're about 3 years too late. So we're engaging really far up in advance with our customers. And I spoke of our systems application engineering team. We have senior technologists and subject matter experts within the R&D organization. They're all working very closely with the advanced development engineering teams of those OEMs and the tier ones. And in that regard, we've become their trusted development partner of choice.
So you have so many things happening very quickly, as we've talked about a few times. So, what advice would you give to design engineers and product managers aiming to stay ahead because we don't want to be left behind in the rapidly evolving field of vehicle sensor technology?
Well, if there's one thing I've learned in my career is that the only thing constant is change. You have to learn to adapt extremely quickly. Do not get comfortable. Stay vigilant. So in TE, we're constantly assessing the market, the technologies that we can choose and develop, our supply base options, the competitive offerings we're competing against. But most importantly, we continuously assess the needs of our customers to understand their problems. Their needs are constantly changing and evolving recently. And in TE, we take pride in helping our customers compete. And by understanding what keeps them up at night, losing sleep, we develop solutions that truly add value. We're the sensor experts, and our customers have come to appreciate being able to partner with us to solve their absolute most difficult sensing needs.
So if people are hearing this and they're saying, you know what, I want to know more, I have some questions, or maybe I don't want to be left behind, as we kind of joked about before, where can they go? What resources can you share? Where can you send them?
Well, we have a website, right? te.com. And you can look up the transportation sensors on that website. If anyone wanted to reach out to me personally, they could hit me up on LinkedIn. I'd be glad to make connections or answer any questions that someone might have. So use your resources.
Perfect. Lamar F. Ricks, Senior Director and Chief Technology Officer, Sensors for TE Connectivity. Lamar, thank you for your time. Exciting, as we've used that word a few times, right? Exciting to see where things are going in the near future. I can't even, it's mind-boggling to think of too far off, but appreciate your time. Great conversation, and thank you for being here today.
Been my pleasure, Michelle. You've been a great host.
Oh, well, thank you. Great guest. Right back at you. And I want to thank all of you for tuning in and listening to our Connected World podcast brought to you by TE Connectivity. And as Lamar said, you can visit te.com for more information there. And be sure to subscribe to the podcast so you can hear more engaging conversations like the one you heard today. Until next time, I'm your host, Michelle Dawn Mooney, and we hope to connect with you on another podcast soon.